In this video, we're going to talk about collision theory. And what collision theory tells us is that if two reactant molecules are going to react with each other, they actually need to collide with each other. And when they collide, they have to collide with enough energy to be able to react. So it needs to be sufficiently energetic. And they also have to be properly oriented. And I will write all of that down here for us in a moment. So, collision theory. A bimolecular. So bi meaning two, so I have two reactant molecules. So a bimolecular reaction occurs when two properly oriented reactant molecules come together in a sufficiently energetic collision. So kind of breaking this down, right? There's two parts to it. Properly oriented, that's important, and then sufficiently energetic. So not all collisions are going to lead to products. Just because they collide doesn't mean they're going to react. They have to collide with the proper orientation and with enough energy. So not all collisions lead to products. Right? Two criteria to it, right? Must have the proper orientation, and I'll show you what I'm talking about here in a moment. And enough energy. And it needs both of those. It's an end. So even if they're colliding in a sufficiently energetic collision, but they're not oriented properly, I'm not going to get the right product. And even if they're oriented properly, but they're not colliding with enough energy, I'm not going to get the correct product. So they have to have the correct orientation and they have to be colliding with enough energy. When that happens, we can then form our products. So an example for us, and I'm just looking at a one-step reaction. Not all reactions occur in one step. We're just going to consider a one-step reaction here. So I'm going to have A, and it's going to react with B bonded to C. And I'm going to form A bonded to C, and then B is going to be by itself. So just a single replacement. So A is floating around, and then B, which is bonded to C, is floating around. And those need to collide with each other. And if I look at my product, A is bonded to C. So if I was to take them and collide them so that B, right, say they bang into each other this way, I would end up with A bonded to B. And if I look at my product, it's not, right? A has to collide with C. So this collision that I just showed, right? Let me grab A again here. A is moving around, B is moving around also. I can only move one at a time, however, so I'm just going to move A and say they bang into each other here. No reaction, right? Because A is not going to bond with B. What I needed to do is I needed to collide over here, right? This would be the proper orientation. So A has to collide with C. It could collide here or here, but it needs to collide with C, not with B, right? If it collided with B, it would not have the proper orientation. And then that has to happen with enough energy because we need to break this bond, right? It needs to be broken. And if it doesn't collide with enough energy, we're not going to overcome that bond, right? We need to put energy into breaking bonds. That energy is going to come in part from that collision. And if I don't have enough energy, I can't overcome it. I always think of that part as like a game of Red Rover. I don't know if you guys played that when you were kids, but you kind of whole bunch of people stand up, right? And you hold hands. You make like a big old wall holding hands. And then someone comes like running at you and tries to break through your hands, right? The only way that person that's running is going to break through is if they're running with enough energy. If you just kind of like walk into it, the kids that are holding hands, right? That bond is too strong that person's not going to get through. Like you have to come running full speed ahead to try to break through those folks that are holding each other's hands. If that's making sense. I hope it is. So correct orientation, enough energy. We're going to go through what's called a transition state. So I'm going to redraw my reaction here. I'm going to have A, and it's reacting with BC. And then before I show the products, I'm going to show what's called my transition state. And I'll write this name down here in a minute. But I'm going to have my bond between B and C. I'm going to draw a dotted line. And then I'm going to draw a dotted line between my new bond between A and C. So a dotted line between B and C, that's the bond I'm breaking. A dotted line between A and C, that's the bond we're forming. And then we finally have our products, right? B is by itself and A is bonded to C. So we said this was called our transition state. And our transition state is our state where we have partially formed and partially broken bonds. So, right, the bond between B and C, I'm breaking it, but in this case, I'm using a dotted line instead of no line because it's partially broken. And then I'm forming the bond between A and C, so I'm using a dotted line again because it's partially formed. So this contains partially broken and partially formed bonds, right? Those are represented by our dotted lines. So those dotted lines are representing bonds that are kind of there, right? Partially broken, partially formed. This is the highest energy form in the reaction. We're going to draw an energy diagram, and my transition state is going to have the highest energy. So our highest energy state might be the easier way to say it. Highest energy state. So the reactants and the products are lower in energy than that transition state. It's actually quite high in energy because we have remember bonds are electrons. So I have all of those electrons kind of around in one spot. So there's a lot of repulsion and things that are happening there. Sometimes it's called an activated, I don't really use this term, but it is in our text, an activated complex. This will be used sometimes in biochemistry. I'm going to generally just call it our transition state because that's what it is. But activated complex is another name for it. So it's the configuration of atoms at their maximum energy. Right, my highest energy states. And we always go through those. We just don't normally show them, right? We usually just show reactants and products. But when they're reacting, there is a transition state, right? It's transitioning from reactants to products. So just kind of summarizing so far, right? We have reactant molecules moving around, right? Or not at absolute zero, so they're constantly moving. They collide with each other. Just because they collide doesn't mean I'm going to form a product. They have to collide with enough energy to overcome the old bonds and form our new bonds, right? They need to have enough energy to overcome that transition state. And they need to have the correct orientation. That transition state is our state where our bonds are partially formed and broken. It is our maximum energy state. It has the most energy that you're going to see in the course of this reaction. Those collisions that do lead to products are called effective collisions. And I'm just going to write it up here, effective collisions. Right? These are the ones that do lead to products. right? These are the ones that have the proper orientation and enough energy. So I want to look at an energy diagram. Sometimes they're called energy profiles. Those really do mean the same thing. I tend to call them energy diagrams, but if you see profile, it's the same. So what this is it's a graph. So a plot of energy versus reaction progress. So if I was to draw one here for us, I'm going to have energy increasing on my y-axis. So down lower is lower in energy, up higher, higher in energy. And then my reaction is proceeding along my x, meaning I'm going to have reactants towards the left, my transition state in the middle, my products on the right. So as I go from left to right across that axis, I'm going, through our reaction. Our reaction's proceeding. Let me write down while I'm thinking about it. Reaction profile or energy profile. So I'm going to start out over here somewhere. I'm just arbitrarily picking a number. I'm going to increase in energy. And then for this one, I'm going to come down further than where we started. So I have my reactants are over here. So R for reactants. This is my product. At the very top up here, this is my transition state, right? Remember, our transition state is our highest energy state. So the part that's, the very highest on my y-axis is going to be my transition state. So TS, transition state, right? My partially formed and partially broken bonds. R was my reactant. P are my products. And again, this is just for a one-step reaction. Not all reactions occur in one step. If they occur in more than one step, you're going to have a transition state for every step. And we'll look at those in a subsequent video. A couple other things I do want to label on here. And one is our energy difference between our reactants and our transition state. That's supposed to be a straight line, but it did not come out straight at all. So this energy difference here, right? So from where my reactant energy is to where my transition state energy is. This is my activation energy. My abbreviation is a capital E with a subscript capital A. Actually, that A doesn't even have to be subscripted. The E does though. Sorry, I didn't mean to erase both. So if you wanted to make that one lowercase, I think that's how our book is probably showing it. I tend to make it capital, but that one's not particular. So let's write that down. Let me add it to our key over here, and then I'll give you our definition. EA. See what I mean? I tend to make it capital. EA, I want to be consistent though, is our activation energy. So we'll define that. And our activation energy is essentially the amount of energy that you have to put into your reaction to get it to proceed, right? You can think of it as the energy barrier to reaction, right? It's the amount of energy, if you're playing that Red Rover game, that kid has to go hurling into those arms with to break through, right? If I don't supply that much energy into it, if I go and look at this, right? At my graph, this is the amount of energy that I have to put into it for my reaction to proceed. If I only put this amount of energy into it, I'm not going to get to a product, right? It would not be an effective collision because I wouldn't have enough energy. So it's our energy barrier to reactions. So the amount of energy that must be supplied for the reactants to react, for the reactants to form products. Right? It's our barrier to reaction. Sometimes it's called the energy hill. I don't really use that one a whole lot, but it's another term for it, right? To get the products, we have to go up that energy hill, right? That's how much energy we have to put into it to get to products. So it's our barrier to reaction. If you put in less than that, it's not an effective collision, no products. So if collision energy is less than our activation energy, no reaction. If collision energy is greater than or equal to our activation energy, we get a reaction, right? If it's less, they just kind of bounce apart. Temperature does affect this, right? Remember, temperature was one of the things that we had said last week that affect the rate of our reactions. Higher temperature, my particles are already moving with more energy, so more of those collisions have enough energy to overcome that energy barrier. One other thing I want to add to this graph, so I'm going back up to my energy diagram, and that's the energy difference between my reactants and my product. Be really careful too on tests or quizzes or homework, or at some point you're probably going to be asked to draw one of these. Make sure that you're clear. I'm erasing my arrow so I can draw it wrong. A lot of times I'll have students, I'm going to make it even more wrong. They won't even draw that line, and then they'll just like do something like this. Like, what is that supposed to be, right? They'll label it. I'll label it in a minute, but it doesn't go, like that arrow is showing that only goes to here, which is wrong, right? It needs to go, oops. It needs to go to here, right? So make sure the end of that arrow hits the line that you want it to go to, not short of it. Otherwise, you're not going that far, right? You're going less to it. And then make sure you have a bottom. And if you stop there, well, you're wrong, because that means you're only here and you want to be here. So make sure, this is nitpicky, but you guys need to do college level work in college. Make sure your arrows, right, go to what they're pointing to. So just be really careful when you're labeling these. I do take off if you're not precise about your markings. I want to know that you know that it's the energy difference between reactants and products. And if your arrow doesn't go from reactants energy to products energy, it's incorrect. So please be careful. That's the same for the activation energy, right? It needs to go from where that transition state, right? It needs to go from here, right? The energy of that transition state to here, the energy of that reactant. So the arrow needs to go to both of those. Okay. Done with my soapbox. What is this one that I was just talking about but haven't labeled yet? What does that represent? That is the energy difference between my reactants and my products. And it would have been something that you would have talked about in 151 in your thermochemistry chapter. Yeah, I'm going to call it our enthalpy change. You might not have come up with that, and that's okay if you didn't. And then I'm going to put a little asterisk on it. For now, we are going to call it our enthalpy change. Later on this semester, I'm actually going to change it a little bit. But remember, our enthalpy change, we're assuming that my only energy, right, difference in this reaction is thermal energy. Then my enthalpy change, right, that was the heat of my reaction. That's basically the overall energy change for my reaction. And again, we're just assuming that all energy here is due only to heat energy. Again, later on in the semester, we're going to change that to something else, but from what we've learned so far, it is going to be thermal energy. So I'm gonna, my little asterisk, we're assuming that all energy that the energy difference, I'm trying to think of the better way to write it, assuming that the energy difference, so delta E for energy difference between reactants and products, is due only to thermal energy, heat energy. If you remember back from 151, we could have work energy also. In this semester, we're going to learn about entropy, and then we're going to incorporate that. But for now, delta H. So my overall energy change between reactants and products, assuming that all energy is due only to thermal energy, is delta H. A quick review on that. We'll scroll down and do that. Right? Remember, enthalpy was the heat of our reaction. So if we have a negative value for delta H, right, what that means is that the heat, my enthalpy final, right, if I'm going to have a negative value, is less than initial, right? Remember, delta H is always equal to my final enthalpy minus my initial enthalpy. Oop. I've been doing a lot of brackets lately. So if I end up with a negative value, that means that my final heat, right, is less than my initial. So if I have a negative value, I have less heat energy when I'm done than when we started, and we gave that a special name. Do you guys remember what a reaction that has a negative enthalpy change is called? Good. Hopefully a lot of you guys got this one. It's an exothermic reaction, right? My system is losing heat energy. My surroundings are gaining heat energy because total energy is conserved, but my chemical system is getting colder, right? It's losing heat energy. Remember, the beaker you're holding on to are your surroundings and not your system. If I have a positive enthalpy change, that means in the end I have more enthalpy, I have more heat energy than when we started. So my chemical system gained heat energy, and we said it was an endothermic reaction, right? Here we lost heat energy. Here our system gained heat energy. So going back up to our reaction here, is this an endothermic or an exothermic reaction the way that I drew it? Compare the energy of your reactants to your products. Okay, remember, energy is increasing up my x-axis. My product energy is right here, right? My reactant energy is right here. So products have less energy than my reactants. So this is for an exothermic reaction. Right, this is exothermic. I'll draw an endothermic one here in a moment, but this one, my product energy is less than my reactant energy, assuming all energy is just thermal energy. This one is exothermic. I always think about this one, this is kind of a strange analogy, but I always think of this one as like going to college, right? Most of us go to college because we want to be more stable, right? Less energy is more stable, right? Higher in energy is less stable. So products in this exothermic reaction are more stable, right? But you have to put a ton of energy into it, right? You just don't go, right? I'm not going to go right from here to here. That green line I just drew and it just disappeared because that's not what happens, right? To go from reactants to products, I have to go up that energy hill, right? I have to put my activation energy into it. So to get more stable, I have to put all of this effort into it, and then eventually we come down here. So I always think about this as going to college, right? We're going to college because we want to be more stable, but this is all the energy and stress and instability that you have to put into it to getting there, right? You put all this effort into it and you're like, well, is it ever going to be worth it? It is, because you're going to be more stable someday, but you have to put that activation energy into it first. So right now you guys are probably somewhere about here on the energy hill. Assuming you're to take organic, that'll bump you up a little bit more, but you're putting that energy into it so you can become more stable someday. Okay, let's look at an endothermic one. So energy is increasing, reactions proceeding. I'm just arbitrarily picking reactants up to my transition state. And then this time I want my my product energy. My line got a little screwy there. I want my product energy to be higher than my reactant energy. So labeling all of this. Still my reactants, still my transition state, still my product. My activation energy is the energy difference between reactants and products. My enthalpy change, it's not a very good straight line. My enthalpy change is the energy difference between reactants and products. But because my products have higher energy, right, are higher in energy than my reactants, this one would be for an endothermic reaction. So exothermic, right? I have less energy than when we started. Products, we have more energy than when we started.